Okay, Bismillahirrahmanirrahim. So let's continue our transformer class. Okay, so now we are into the equivalent circuit of the transformer. I think last week we covered the transformer losses. Okay, so actually the losses must be considered in order to generate the equivalent circuit of the transformer. Okay. Okay, so there are 4 types of losses, and since we know that we have 4 types of losses, that means that we will have 4 component. Okay, 4 component in the losses in the circuit. Okay, so we have a copper losses. So we know that the copper losses basically is only based on the resistor, okay, and then it convert to the heat, okay, where we know that the losses, this is the losses is power P equal to I square R. Okay, so this must be element, one of the element must be inside in the transformer. So we know that the basic transformer, okay, this is just a basic transformer, transformer equivalent circuit, just a basic or the ideal one. Okay, this is V2, this is V1. Okay, so this is N1, this is N2. Okay, so this is a basic. So we need to put some parameter or the element into the circuit. So now we have the copper losses. So copper losses consists of the resistor. So we need to add one more resistor. Okay, we need to add a resistor. Okay, we need to add a resistor. For example, we add resistor in here. So we name it as a R1. Okay, and then we move to the leakage first. Okay, we move to the leakage first. Okay, because leakage and losses, the end core losses is depend on the current flow into the core, current flow into the wire, and then conduct the magnetic flux. Okay, so we assume that the will flow into the flux into the core. Okay, so then they will be inside the in series. Okay, and then for the eddy current and hysteresis, there will be another branch. Okay, it's like a parallel. Okay, so leakage flux. For leakage flux, how we want to consider or design the equivalent circuit for leakage flux. Okay, so first of all, we need to see the equation. Last week, okay, we cover I think here, where is it? Okay, we see the leakage, this one. Okay, still remember this one? So we have a 2 component, ataupun kalau dia punya gambar tu. Okay, yang ni. Okay, so we have a mutual flux and then we have a leakage flux. Okay, we have a leakage. Okay, so this leakage, so this is the component. Okay, this is the component. This one is for primary side and this one is for the secondary side. Okay, so we take this part and we try to design the parameter. Okay, so over here you can see, okay, we already extract it. Okay, we take it the formula, okay, for the leakage flux for primary and also for secondary. Okay, and then we need only this one, we need the flux LP. Okay, so in order to get this one, so we need to integrate. So we need to integrate this part and then integrate this part. Okay, so then we can get the this one flux. Okay, and we know that the flux, okay, we know that the flux is proportional to the current, okay. So from the, still remember that the formula of the flux. So we have a BA, okay, flux equal to BA, okay, and then ini semua kita belajar dekat I think chapter 1, not here, okay. So remember that yang this one, flux equal to BA, okay, and then B equal to mu H. H equal to apa? H equal to apa? HL over N equal to Ni, right? So if we replace B, we replace here, and then we have H, we replace here, so it will directly proportional to the I, okay. So however for the flux, yeah, of course bila kita tukar tu dia akan ada mu Ni over L, okay. So ni lah, so they will be directly proportional to the current, okay. So however this one is there is a different parameter lah for flux, okay. So there will be only, they use a permeance, okay, they use a permeance of flux path, okay, the times with multiple number of turn and also the current. So which means that the flux is proportional, directly proportional to the current, okay. So yeah, in order to get the I, in order to integrate the flux, we need to have something non-parameter, so which is the current, okay. So otherwise from here it's difficult to differentiate the flux. So now we replace, okay, we replace this equation, okay, we replace this equation into this equation, okay, we replace the flux, okay, this flux here into here, okay. So then we can get the new equation, okay, this one, okay. So you can see that the ELP, the induced leakage flux, okay, the induced leakage flux is equal to number of turns square at the primary times with the permeance of flux path, okay, times with the rate of change of the current, the current rate of change, okay. So from here we can see that this part, okay, so since the induced current, induced voltage is proportional to the differentiation of the current, okay. So which means that they will be lag, okay, so mean lagging, so lagging from the voltage. So the thing is lagging, okay, from the voltage actually is the voltage, the inductance, okay. Kalau kita tengok last week kita dah belajar kan, yang last week we cover that the voltage is like cosine, okay, like a cosine wave, and then the flux is sine wave, okay, still remember, okay. So this one is flux and this is a sine wave, okay, cosine. So flux lagging, okay, lagging from the voltage, okay. So the thing lagging here actually is the inductance, okay, we know that the inductance is lagging, so that we replace this one, so LP equal to NP square with the permeance, okay. So this is the new equation, simplified equation, okay. So that we know that the inductance, so this is inductance, okay. So since we know that the parameter is inductance, so then we can convert it into a reactance, okay. So what is the relation between the X, which is the reactance, with the L? What is the relationship? Macam mana kita nak kira resistance ataupun dipanggil reactance in term of the inductor. Ni nampak ni dia punya equation omega L P. Okay. So however, all of this no need to remember. Okay, you just need to know where it come from. Okay, where the equation come from. Okay, so this is xs equal to omega ls. So then this kind of reactance, okay, we know that this is the reactance, so that we can add into the design into the circuit. Okay, okay, I forget. So since we also have a second core, and so we have a R2, okay, and this one we add the reactance. So this is x1 and this is x2. Okay, so now we cover already the copper losses and also the flux leakage. Okay, flux leakage. And then how about the eddy current and also hysteresis losses? Okay, okay, this one is little bit more easy. Just look into the graph. Okay, okay, so this is the total. This is the excitation current. Still remember? Okay, still remember? This is the excitation current. Excitation current Im plus I H plus E. Okay, so we need to design for this. So since they have a two junction, okay, they have a two component here. So this is like a parallel. So parallel, we need to do like this. So we have a two component. Okay, we don't know which one, either resistor or inductance or capacitance. We don't know. So what we know is it's like a junction. Okay, this is I excitation. So this one is Im. Okay, and this one is I H plus E. Okay, so then we can multiply with the component. So to know the component, we need to separate. Okay, this is the I excitation. We need to go to the detail current, detail graph. Okay, so for this one, for IH, okay, eddy current and hysteresis losses, so we can see that the IH is in phase with the, so the dash line here is the voltage. Okay, it's actually in phase with the voltage. The I is in phase with the voltage. So since it is in phase, so we can assume it as a resistor. We can assume as a resistor. Okay, so the component here we can add is a resistor. Okay, where we call it as a RC. Okay, and then for the Im. Okay, so this one Im. So you can see that this is a sine wave. Okay, sine wave. Flux is sine wave. V voltage is cosine wave. Cos wave. Okay, so you can see that the Im is lagging. Okay, again Im lagging. So again, when anything lagging, it will related with the inductance. Inductance. Okay, inductor. Okay, or inductor. So you can say, you can put it as a component L. Okay, so however we cannot directly put L, we can write it as a XM. Okay, so omega Lm. Okay, so this component we will put inside the parameter. Okay, so this is the XM. Okay, so and then where to put this junction? Okay, so this junction where we can include the whole component. Okay, I think we can put it. Alamak, ini kecil sangat. Okay, sebenarnya kita boleh letak sini, dia dekat sini. Okay, sini and then junction tu. Okay. Tak apa, saya lukis dulu, nanti saya tunjuk lah. Okay. So this is, for example, this is RC and this is XM. Okay. So after we know already all everything, so this is the complete. Okay, this is the complete transformer equivalent circuit. Okay, so this is the component circuit lah, equivalent circuit. So we have a RP, which is represent the copper losses, and then XP will represent the core losses. Okay, core losses, flux leakage. Okay, for the primary side, and this is core losses in the secondary side, and this is the secondary side of the flux leakage. And then for the excitation current, so this is I excitation. Oh, tak nampak. Okay, for excitation, so excitation, this is I excitation. I excitation, this is I apa yang lalu ke RC ni? I apa yang lalu ke RC ni? Sebab kita ada dua I ni. So kita know IM plus IH plus E. So this one is what kind of I? Ingat tak? Baru kejap ni.
IP.
I apa? IP. I apa? Tak dengar lah. Tak clear. IM lalu dekat mana? Dekat SM. So ni IH plus E lah. Okay. So then ni IP lah. Ni IP. So IP dia tak lalu lah. Dia bukan tak lalu, dia akan pecah lah. Okay. Okay, so once we look at this equivalent circuit, this one we just can design only, yeah. Okay. So we can design, okay, this component is here, okay, this component here, this component here, this component here. Okay. Asal awak tak nampak mouse saya ke? Oh, tak nampak mouse Tahu-tahu melukis kat situ. Okay. Mouse ada tak? Oh, ni ada pula mouse.
Ada doktor.
Okay. So once we know already, so this is the equivalent circuit. What we can do with this equivalent circuit? Okay. So we cannot do anything with this kind of equivalent circuit unless we make some assumption, and also we need to refer to only one side, okay, either in primary side or in the secondary side. Then they will be meaningful, so that we can do an analysis. Okay, so this is just a equivalent circuit and just like a background only, yeah. So we cannot do with this. We cannot calculate or analysis with this kind of circuit. So we need to do some assumption and also the transfer to the one side, either primary or the secondary. Then we can do analysis. Okay, so then as I mentioned, we need to refer, we need to translate. Okay, so this one, so this circuit, saya zoom dulu lagi. Okay, first one, we refer the secondary side to the primary side. Okay, so we know that this one is the, we can name it as a R S prime. Okay, is equal to A2 R2. Okay, and this one is X S prime. So this is R S prime. Okay, so X S prime is equivalent to A square X square. Okay, and this is, we can write another way. So this is equivalent to Vs prime. Okay, and this one also you can write as a Is prime. Okay, doesn't matter lah, you nak tulis apa pun boleh, tak ada masalah. Okay, yang penting you tahu kira je lah. Okay, Is prime is equal to Is over A. Okay, so Vs prime is equal to AVS. Okay, so this is important. So jangan terlupa cara calculation dia. So this is very important. So this is the way how from the secondary side to refer. You refer to the primary side. Okay, and then the below one is you transfer the primary side to the secondary side. Okay, so this is a VP prime. Okay, so this is the RP prime, and this is XP prime. Okay, and also this one also you need to transfer. Okay, equal to XM prime. Okay, so later on in the exam or in the quiz, okay, no need to write the equation over here lah. You can write just prime lah. Okay, prime, and but you need to write the full equation somewhere else lah. Okay, maybe at, for example, like this lah. You write here, you write here actually the, tak nampak. Okay, you write here Rs prime, then you write somewhere else Rs prime is equal to what? Okay, so you need to do like that. Okay, don't just directly put prime, but what is prime you don't know. You didn't write, so cannot. Okay, so this is the way how we convert from one side to the another side. Okay, however, so this junction, okay, this parallel part here at the center, okay, this parallel part here make us difficult to do the analysis. Okay, this kind of part is make the circuit become complex. Okay, become complex, and then difficult to calculate. Okay, and then we need to see what we can do with this kind of parameter. Okay, so either we can remove or we can move to another one, to another place. If can, why? Okay, so this is the question that we need to answer. Okay, okay, so in order to make it simple, okay, in order to make it possible to calculate, to do the calculation, to do the analysis, one assumption we need to know actually is like this. Okay, they said it's more complex with the junction. Okay, so they say one of the principal complaint about them is that the excitation branch add another node to the circuit being analyzed. So then become complex. How become more complex, difficult to analysis. So you need to do the parallel things, blah blah blah. Or maybe you need to use Thevenin. So very complex. Okay, so we need to know that we can see about the current. Okay, so the current can tell us everything. So they say that the excitation branch has a very small current. Okay, small current. Okay, has a very small current compared to the load current of the transformer. Okay, so it's about 2 to 3%. Okay, so they say this is true, and we can simplify. We can simplify the equivalent circuit. Okay, so we can move. Okay, we can simply move to the front of the transformer. Okay, you can see here. So masa tak gerak ni? Oh, jam dah. Okay, so we can move. Before this is here, is somewhere here. Okay, somewhere here kan. So we move it to behind of the copper losses. So it is because of the number of current. Current flow over there is very small. Okay, so yeah, once the current flow is too small, it can show you that the resistor is very high. Okay, the resistor is very high, so therefore the current is low. Okay, so you can directly move to the back. Okay, you can move to the back. Okay, so yeah, this is the equivalent for the combination for the primary side. Okay, this is the primary side, and this one is the secondary side. Okay, this one is secondary side. Secondary side. So this one already refer to the secondary, refer to secondary side. So this one is refer to primary. Okay, so this is the two different things. So jangan ingatkan dia bergabung tau. Ni bukan So this is different and this one is different Kerana A dengan B dua different things It's not the same. Okay, so then we can remove. We can just ignore the junction already. Okay, so we just can ignore the junction. So just become like this. So it will be like this only. Okay, this one is the primary side. Okay, refer to the primary side. Okay, refer to primary side. Primary side, and this one is refer to the secondary side. Okay, so yeah, in total they just write equivalent R equivalent S, X equivalent X. So this is the R equivalent S, this one is the R equivalent X equivalent X. So this is the R equivalent P, this is R equivalent X equivalent P. So since it already become in series, okay, so from this one, so we remove this part. Okay, remove the center part. Okay, we remove this part, and then everything become in series. Okay, so we can add this one, we can add this with this. Okay, and the X with the X. Okay, so until now everybody understand? Boleh faham tak tentang equivalent circuit from how from the beginning how we assign each parameter from the leakage, and then the copper, the current, the excitation current, eddy current. Okay, so and then we design the equivalent circuit, and then from the equivalent circuit we know that the current is small to the junction, so that we can remove or ignore it. Okay, can ignore and then become in series current, in series circuit current in series, circuit in series. Okay, so and then we also know how to transfer from the primary side to secondary side, secondary to primary side. Okay, so boleh faham? Do you understand until now?
Faham, Doktor.
Okay, cantik. Alhamdulillah. So now, yeah, if we design the parameter, we know the number of resistance. Okay, because we design it. Okay, so however, sometimes we just buy. Okay, we buy the transformer, and then it's like a black box. Okay, we don't know what is the value for the resistance, the RS, RP, XM, XP. We don't know. Okay, we don't know everything. So we need to do the test. Okay, so we need to do the test for the transformer in order to determine the value of component in the transformer model. Okay, So there are two types of tests that we can conduct. Okay, before that, I think better we go to the example. So better we go to the example. Okay, so this one just test you how to transfer, how to calculate. Okay, so a step down transformer. So how we know to step down? So first of all, we need to see the primary side. So primary side is higher. So this is high voltage and this is a low voltage side. Okay, so this is primary and this is secondary. Okay, as the following parameter. Okay, this one is given already. The RP, XP, RS, and this is the RC. Okay, this is RC. Okay, and they say find the equivalent circuit winding impedance refer to the high voltage side. Okay, so we need to calculate to the high voltage side, which is the primary side. Okay, it will be like this. Okay, this will be this one. Okay, so this one will be Vs prime, Xs prime, Rs prime, Xp, Rp, Vp. Okay, because this is the refer to the primary side. Okay, high voltage side. Okay, so now we need to calculate the Rs. What is Rs? So Rs prime is equal to A square Rs. Okay, Xs prime A square Xs, and then Vs prime equal to AVs. Okay, so then we just calculate. Okay, and then we will get the value. Okay, so since there is no so this is the Vs. Okay, this is a Vp. Okay, so then we can know each other. We can know the value. Okay, so firstly we need to get the A, and then yeah, this one they just directly so dia tak buat for me I not combine yet. Okay, so later on you can combine. So R equivalent P is Rp plus Rs prime. Okay, and then X equivalent P which is refer to the primary side, Xp plus Xs prime. Okay, for me I comfortable using the prime. Okay, compared to you just directly A square Rs. So sometimes you confuse. Okay, so we just put everything, and then you will get the R prime and also the X prime, and then for Z is just you add together the X and R equivalent P plus X equivalent P, so J like this. Okay, so then they say refer to the low secondary side. Okay, low secondary side. So we draw first what component consists. Okay, so this is a Vs, this is a Xs, this is a Rs, this is a Xp prime, this is Rp prime, this is a Vp prime. Okay, so Rp is what? Is equal to Rp A square. Okay, and then Xp prime equal to Xp over A square, and then Vp prime is equivalent to Vp over A. Okay, so therefore I said better you do like this because otherwise you confuse either A square times Rp or Rp divided by Xa square. So you need to familiar with this kind of calculation, with this kind of equation. Okay, and then you just add everything. Okay, just add got the equivalent, x equivalent, and also the z equivalent. Okay, faham boleh faham
Boleh, Doktor.
tak ada masalah buat
Faham,
ni
Doktor. Faham, Doktor.
Okay, bagus. So alhamdulillah. So and then kita dah tahulah tentang equivalent circuit. We know already the equivalent circuit. Okay. So now as I mentioned, we need to find the parameter or the component, the value of the component. So there are we know that the equivalent circuit, it consists of the resistance and also the reactance. Okay. So and then we can do two type of tests. Okay, the first test is the open circuit test. Okay, the first one, and then the second one we do the short circuit test. Okay, so actually by default this kind of test I should give to you to study by yourself. Okay, because we already make it as a project. So the project will be a student-centered learning. Okay, so however it's okay, I will explain here, so later on will be easier for you to conduct the project. Okay, so yeah, let's go to the open circuit test first. Okay, so this one, that open circuit test is we supply the voltage at the primary side, and then for the secondary side we left it open. Okay, so at this time we can supply a full rated voltage, doesn't matter, don't worry. Okay, because it's open circuit, we can full swing. Okay, we can make it maximum voltage. Okay, so since the second one is open circuit, so the current will be almost zero. So tak ada masalah. So we can supply full voltage, doesn't matter. Okay, so however for the short circuit test, okay, so for the short circuit test we supply the voltage at the primary side, and then for the secondary side we just make it short circuit. Okay, so however, so at this kind of test, short circuit test, we must use a very low voltage source. Okay, so however when we use the low voltage, so we need to adjust the current so that the current will be the rated value. Okay, will be the rated value. Okay, for example, you use a voltage, rated voltage, and then you can supply rated current. Okay, so that one is if you have a load. Okay, but for short circuit test you must use a very low voltage. Okay, and then you adjust the current, so that become the load or the rated value of the current. Okay, so yeah, sometimes even though you use a low voltage, okay, low voltage, but the process is short circuit, so current will be higher. Okay, okay, so otherwise if you use the high voltage or full rated voltage during the short circuit test, for sure everything will become barbecue. Okay, so will burn up. Okay, so you need to be careful. Okay, so however during the test, since you are using simulation, so you can put whatever voltage you want, but in the real life you cannot. Okay, you cannot. Okay, so for the open circuit test, okay, so we do the open circuit test, and what we can get. Okay, so all the input current must be flowing through the excitation branch. Okay, so the series element Rp are too small. So the value of Rp is very small. Rp and Xp are small compared to the Rc and Xm, to cause a significant voltage drop. Okay, so since we supply the voltage, we ignore the current. Okay, we assume the current, not the current, the voltage drop. Okay, so for example this one, so we supply, and then kita ada resistor, this one, and then the excitation branch. Okay, so by default that this voltage will be less lah. Okay, so this kind of voltage, kalau kita ambil voltmeter, okay, voltmeter here, okay, so of course they will show you V here is less than P ya. Okay, betul tak? Because of voltage drop. Okay, because of the voltage drop. However, since the value, so this value is small. Okay, value is very small. The value is small. So the voltage drop, okay, the voltage drop here is very low. Okay, so we can assume that the V here, okay, at the branch is equal to the VP. Okay, so because the value is very small, so the voltage drop is not significant. Okay, it's very low, so we can ignore the RP and XP. Okay, so then we can do the calculation for RC and XM. Okay, and then what we can get from the open circuit test. Okay, so we can get the parameter, we can get the power factor, and then the magnitude lah. Okay, so once we get that, we can know lah the imaginary part and also the secondary, the imaginary and the real part. Okay, and then for the short circuit test also the same, we can get the power factor and also the magnitude lah, the series impedance. Okay, so this is the open circuit test. So open circuit test, we can say something like this. So this one left open. Okay, and then we supply the voltage, and then we measure the voltage. So we measure the voltage, and also we measure the current. Okay, so in order to get the power easily, so we just use the wattmeter. Okay, so we just use the wattmeter. Okay, so this is the setup. Okay, this is the setup. Okay, so since the branch, okay, the branch is parallel. Okay, the branch is parallel. Okay, so this is RC, this is XM. Okay, so how to add together? How to add the resistor? For example, resistor. How to add the resistor while the circuit is parallel? Macam mana nak add? Kalau in series kan kita just tambah. 1 over, okay, it's good. So we will get that, for example, R total. R total is equal to 1 over RC plus 1 over XM. Okay, so XM dia ada J sebenarnya ni, ada J. So kita letak J. Okay, so then in order to make it more easy, okay, in order to make it more easy, so the 1 over T, we name it as a YE. Okay, we name it as a YE. Okay, and this part, we name it as a GC, and this part is plus, plus. Okay, remember, this one is plus. So the J is at below. So in order to make it reasonable, so 1 over XM is BM. Okay, so however they will become BM over J. Okay, but they plus kan. So then we can to convert it, to make it more reasonable, more suitable, okay, so we can take it up lah, okay, so kita boleh naikkan dia, kita naikkan J, so it will become minus J BM, okay, so from here divide by J, so now become J BM, however the sign will be changed, J BM, okay, so then we get this kind of equation. So this kind of equation is from the additional of the parallel resistance, okay, or reactance. So that is resistance and also the reactance. So impedance lah, the impedance. So yeah, it's from the parallel side. So since parallel, so this is kind of the equation. So therefore they become like this lah. Okay, so then how to measure? That is the question. How to measure? How to get use of the voltmeter, wattmeter value? Okay. So in order to get the YE, so we need to remember YE is 1 over RT. Okay. So if you use the Ohm's law, so Ohm's law, V equal to 1 over, betul, 1 over pula, V equal to IR. Okay, so if you measure the R is the impedance kan, so it become V over I. So this one is I over V. Okay, I over V. So it is because of 1 over R. So kena ingat it become 1 over R. Okay, so 1 over R is equal to YE is equal to I over V. Okay, so so since we have a bacaan the reading during the open circuit test, so we just use the reading so I over IOC and VOC. Okay, and then for the power factor, okay, we just directly use, okay, because of power, okay, power from this equation VOC IOC cos theta. Okay, so from here we can measure the power factor. So the power factor is equal to cos theta, cos theta, and then from here we can calculate the subhanallah, the PF, the angle. Okay, the angle ni tak ada apa, tak ada negatif. Okay, so yeah, why we want to measure the power factor? Because we want to measure the angle. Okay, so and then from here so then we can get the angle. So once we get the angle, we must to know that the I excitation is lagging. Okay, kena ingat I excitation tu lagging tau. Secara total tu dia dalam bentuk seakan-akan sine wave. Okay, okay, I excitation, mana graf dia? Okay, I excitation ni, so this is voltage kan, so this is voltage, voltage, so this is the I excitation. Okay, I excitation, so I excitation we can see is lagging from the voltage. So since the voltage is lagging, so we need to add negative sign in front of the angle. Okay, so YE equal to IOC divided by VOC. The angle is negative. We need to add this. Okay, don't forget to add the negative sign because it's lagging. Okay, so this one is lagging. So from this gambar, from this figure. So then yeah, that's all for the short circuit test. Okay. Okay, so once you get this, okay, once you get this, you will get the YE GC minus JBM. Okay, so you get this two component. So this is 1 over RC and BM is 1 over XM. Okay, and then from there you can measure the RC and XM. Okay. So this is the imaginary. So later on you need to put the calculator, assign your calculator in complex mode. And then for short circuit test, okay, so the difference only at this side. Okay, this side is only the difference. Okay, short circuit. Okay, and since the voltage, so we use the voltage is very small. Okay, this one, the voltage is very small. Okay, and current flow into excitation branch is negligible. So kita boleh remove, kita boleh ignore current yang melalui excitation branch. So excitation current we can assume is equal to 0. Okay, so and then we just take note or calculate only at the RP and XP. Okay, or they are equivalent. Okay, or the series impedance only. Okay, so now we can use directly Ohm's law. So Ohm's law is V equal to Iz. You can say Iz. So Z equal to V over I. Okay, so V short circuit, so I short circuit. So from the reading, okay, so that one is the magnitude, and this one is from the wattmeter to calculate the power factor. Okay, so from here we can get the theta. So and then the VC, so VCS value, the phase is 0, and the ISC is lagging. Okay, remember the ISC is lagging, and then it's like when we want to combine each other or to add the phase, so it become 0 when we menaikkan dia ke atas. Okay, become plus theta. Okay, so then become this one 0, 0 become theta only. Okay, this is not, don't say that there is no negative sign because it's leading, okay, or in phase. No, not like that. Actually you need to add this one, add below. Add below. I think you can calculate, you can try press your calculator. Try to press your calculator. Okay, yeah, whatever you can try buat macam ni. Okay, so again, once you get this one, the ZE will come out the real and imaginary part. Okay, part the imaginary. So the real part is the R equivalent, equivalent at primary side, and I imaginary is the X equivalent at the primary side. Okay, so like this. Okay, it become like this. Okay, so we know that the RP, R equivalent, okay, is this equation, and the X equivalent circuit is this equation. However, yeah, since we do only limited tests, so short circuit and also the open circuit test, it is difficult to know every resistor, RS, what is RP, what is RS, what is XP, what is XS. Okay, it's very difficult. Okay, so we just normally we just leave until this part. Okay, just leave until this part. Okay, so unless they bagi tahu lah, okay, unless they give you some clues, mention that the RP is 10% from the secondary side. Okay, so then you can calculate over there. Okay, suara dah nak hilang lah ni. Okay, so this is the example. I think better kita buat kita try to do the calculation. Okay, so before that, I think better I take a screenshot. Okay, please get ready with the pen and pencil. Okay, I really want all of you calculate together with me. Okay, yeah, I can show you the result, but that is not a very good way of study. Okay, so I want you to see how to calculate it. Okay, so yeah, this is the yesterday class. You can see from the OneNote here. This is from the yesterday class. Okay, I already did during the class. Okay, so now I do it for you. Boleh nampak tak ni? Okay.
Boleh.
Now where to start? Now I want you to advise me where to start. Siapa tadi kat Putri Zalia?
Nampak.
Saya tak tanya nampak ke tak. Okay, please advise me. So from where to start? Bagilah respon sikit. Ni kalau kat kelas ni saya dah panggil lah. So datang kelas.
Open sikit dulu.
Open sikit, okay. Open sikit test So open. Okay, open sikit test. Apa yang kita boleh buat dekat open sikit test ni? Kita ada YEB pula. GC minus JPM. Betul tak? So untuk mudah kita terus calculate dia punya power factor. We calculate the power factor first. Power factor is equal to apa? POC, VOC, IOC. POC berapa? 400, 400. VOC 8K. And then IOC 0.214 volt. Okay, siap tulis volt lagi ni. Okay, special. Okay, berapa jawapan? Ni suruh student kira ni. Kalau tak kira ni tidur nanti ni. Cepat. Saya tak ada jawapan ni. Saya tunggu student kira ni.
Sekejap, Doktor.
0.23.
0.23.
0.233.
0.233.
Okay, 0.233. 33 berapa? Kita ambil 4 lah.
6.
0.233.
Dah siap bunda belum?
Dah.
Okay, 6. So now we know that the power factor, the value of power factor. So this power factor, lagging ke leading? Lagging atau leading? Atau in phase?
Leading.
Leading. Mampus. Leading. Leading ke lagging? Penat tadi kita
Lagging.
Penat tadi kita tengok kat sini tau. Penat tulis kat sini lagging Power factor ni lagging, jenis yang lagging. Okay. So because of the current dia, okay, dia tak in phase, dia sine wave. Okay, so kita tulis siap-siap lagging. Okay, bukan lagging seluar tu, lagging lambat, macam terlambat. Okay. So and then we can calculate the theta. So what is the theta? 0.2336. Okay. Berapa ni? Betul lah. Berapa? Cepat.
76.49.
Lama. 76.49.
Yes.
Okay, thank you. Okay. So we know that the power factor is lagging. So we know the value of phase, the angle already. So please be reminded that don't forget to add the negative sign during the further calculation. Okay. So now we want to calculate the YE. So YE Okay, YE is equal to YE equal to apa? IOC kan? IOC VOC negative theta. Am I right? Betul ke tak betul ni?
Ya, betul.
Okay, good. Saya nak tanya, nak try ni. Okay, so then kita just put everything 2.14 divide by 400 pula. 8k, and then don't forget to put the negative sign for 9. Okay, and then what we get? What is the answer? What is the answer? Come on.
26.75 micro.
Okay, that one is I don't know what to say. That one is this one. That one is like this. That one is in macam mana nak cakap Saya pun tak pasti dia punya term tu apa. Try to make it into the real and imaginary part. Try to extract it. I know that you mean that this one has 0.0000268 minus 76.49. Am I right?
Boleh saya try tu?
Okay, so now apa dipanggil apa? You try to open it. Okay, you must have the imaginary and real and imaginary part.
6.249
Micro
exponent negative 6.
negative
6.249.
So 0.000 berapa banyak zero ni? 1, 2, 3, 4,
0.550
63 minus
62
tak apalah,
exponent
and then minus
minus 2.6
J
negative 0.000 0 ada 4 26
and then 26. So this one, okay?
Yes.
So this is the YE. Okay, so we know that this is the GC. Okay, and this is the X pula. This is the BM. Okay, so now we calculate the GC, the X. So we know this is 1 over RC and this is 1 over XM. So now we calculate the RC. RC is 1 over GC. Okay, 1 over 0.0000063. Berapa dapat? Okay, I think dapat 100 k ohm Okay, RC and then XM 1 over BM. Okay, so 1 over 0.000026, so equivalent to 38.4 k ohm. Okay, so this is the XM. Okay, so nampak tak dia punya flow calculation tu? Simple je sebenarnya, sangat simple. Okay, the trick ataupun the ramai many of the student make a mistake here. Okay, student forget to put negative sign. I sing pula sign. Okay, student forget. Okay, so yeah, sometimes they forget because they didn't understand the current in phase or in the leading and also the lagging. Okay, so we know already the XM and the XC. Okay, So now we want to calculate the other part or the short circuit. Okay, short circuit test. Okay, now short circuit test. I think in your project also you will conduct the same thing. Okay, but you will have the real not the real simulation simulation using the MATLAB. Okay, so now we move to the short circuit test. So what is the calculation involved? Okay, so as I mentioned before, the first thing or the easiest thing to calculate is the power factor. Okay, power factor P short circuit divided by V short circuit I circuit. Okay, 200 watt divided by 489 2.5 current ampere, then become berapa dapat ni? 0.198. Okay, remember it's lagging. Okay, and then calculate the theta ataupun kalau you tak nak tulis theta pun, tak nak calculate theta dulu pun tak ada masalah. You can directly go to the Z. Z short circuit equivalent. So this is VSC divided by ISC. Okay, and then you can directly put the cos -1 PF. Okay, you can directly put like this. Okay, or if you want to make it step by step, you want to calculate the theta and then step by step, okay, no problem. Okay, so this one try to settle. This one, what is the value here? 58.7. Okay, 58.7. So then we will get the 38.3 plus J192 ohm. Okay, so this is ZSE. So we know that this part is the R equivalent and this is the X equivalent at the primary side. Okay, so we just rewrite the prime and 38.3 ohm. So very small 38.3, and this one is equivalent 192 prime. Okay, so how I know the R equivalent at the primary side? Okay, is based on the question. So the question mentioned that the impedance of the approximate equivalent circuit refer to the primary side. Okay, they say the test performed on the primary side. So the test is performed on the primary side. Okay, so whatever result you get is the equivalent circuit at the primary side. Okay, so if the question mentioned that the test is conducted or performed on the low voltage side. Okay, low voltage side mean that you need to refer here which one is more lower, either 8K or 240. So 240 is the low voltage side. Okay, or the secondary side. Secondary side. Okay, so sometimes secondary side is higher compared to the primary side. Okay, so far faham tak kat sini? Faham tak? Do you understand?
Faham, Doktor?
Faham, Doktor.
Yes, Doktor. So yeah, before we continue, okay, 2.7 is removed from the syllabus. Okay, so we not cover. So this one, the per unit system, we not cover. We will not cover. So we later on we try directly to 2.8. Okay, so however we take a break. Okay, we take a 10-minute break. Okay, I think I will lose my voice after this. Okay, I feel very dry. Okay, so we take a rest for 10 minutes. Okay, so we meet again at 12:26. Okay, okay everyone.
Okay,
Okay,
Doctor.
okay. Alright, Doctor. Thank you.
Okay, let's continue. So yeah, just now we just finished about the determining the value, the component value. So now we want to measure the regulation, voltage regulation, and also the efficiency of the one of the transformer. Okay. So yeah, full load voltage regulation is a quantity that compares the output voltage. Okay, compare the output voltage of the transformer at the no load, i.e. okay, at no load. So which means like an open circuit, no load. So it's like this, So we measure the output. So we measure the output means that we need to refer the circuit to the secondary side. Okay, so this is the V over A. Okay, and then this is R equivalent S, and this is X equivalent S. Okay, secondary kan. Okay, this is the VS. Okay, so when is no load, so no load means that the current is 0. So current is almost 0, and we can assume that the Vs is equal to Vp over Va. Okay, we can assume, okay, so that this is the voltage regression equation. So where is the Vs at the no load minus Vs at full load divided by Vs at full load, okay, and then times by 100. So here, so Vs as no load, we need to consider this one, okay, this kind of circuit. Okay, we assume the current, there is no current flow, and then we assume no voltage drop, so that Vp equal to Vs. Okay, so we just replace, here is Vp, we just replace with Vp over Va. Okay, so this one. Okay, so it's more easy to calculate. Okay, because sometimes during the test, they didn't mention the no load voltage, the no load value. They just mention the full load voltage. Okay, so full load is the given supply, the supply one. Okay, so yeah, this one. Okay, so and then with this circuit, we do the KVL, Kirchhoff voltage law. Okay, this one macam ni. Okay, so Kirchhoff voltage law, KVL, and then we will get this kind of equation. We will get this equation. Okay, so for the voltage regression, we can make some assumption, early assumption, whether the voltage regression is it positive or negative. Okay, we can early prediction. Okay, and also we can do some calculation. Okay. Okay, so this one, I think better I put it blank first. So we assume the power factor. Okay, firstly we assume the power factor is lagging. Okay, so since we refer the output voltage, so the output voltage become the reference. So Vs, the phase is 0. Okay, the phase of S is 0. Okay, so this one is 0. Okay, and then we know there is a current, the Is. Okay, so the Is power factor is lagging. Okay, so then we know the lagging. So ni lagging maksudnya negative kat sini. Okay, so this one is Is. Okay, and then what component S we have? So we have already Vs, and then we must put here Is multiplied with the Re. Okay, we need to continue over here. So this one just to show the angle, the phase. Okay, this is Is times R equivalent. Okay, and then this part. Okay, so this part is always 90 degree with the always 90 degree okay, always 90 degree. Alamak, tak 90 degree ya, boleh lah. Always 90 degree So this is the Is x equivalent. Okay, and then we just continue connect to the end over here. So this is the P over A. Okay, so from here we can see that the Vp over A is more than Vs. Okay, we can see the Vp over A is more than Vs. Okay, so I can show you the real one. Okay, so this is the lagging power factor. Okay, and then for what happen when the power factor is unity. Okay, so we know that already the Vs is the reference, and the Is is in phase with the Vs. Okay, and then we just plus the vector because the equation is plus. Okay, equation is plus the plus. Okay, so Vs plus with the Re equivalent multiplied with the Is, and then this one is always 90 degree, the inductance component. Okay, Xe equivalent Is, and then connect. So this one also you can see that Vpa more than Vs. So what happened when Vpa more than Vs? Okay, so we can know already the voltage regulation is positive. Okay, when Vpa over A more than Vs, so the voltage regulation become positive. Okay, voltage regulation become positive. Okay, and then this one when the power factor is leading, when the power factor is leading, so we draw a V. Okay, we draw a V first, and then we know the current is leading. Okay, so we just multiply. So this one is same direction, same angle with the Is over here. Okay, so Is Re, and then this one 90 degree. Okay, the X equivalent Is, and then we connect the Vpa phasor. Okay, Vpa over Va. So we can see over here that the Vs, Vpa less than Vs. Okay, so we can know that the voltage regulation will be negative. Okay, so bila kita tahu dia besar kecil, kita masukkan dalam equation ni sebenarnya. Okay, so because it's minus so because minus, so if this one is more than this, okay, this one bigger than this, so become positive So if this one smaller than Vs, so become negative. Okay, so the voltage regulation supposed to get I think the base is 0 Okay, because no voltage drop. Okay, so now to measure the efficiency, the efficiency is one of the most easiest equation. So you can write N like this equal to P out P in. Okay, P out P in darab 100. Okay, actually that's it. Okay, you can just directly put like this, or we know that the P in, okay, we know that P in is equal to P out plus dengan any losses. Okay, any losses we can add it together, so then become P in. Okay, and then you can also put the this kind of equation, VSIS cos V cos theta. Okay, so and then there are few more losses, copper losses and also the core losses. Okay, so this is the example. This is an example. I think for this part I will make it short. Okay, wait, I think I need to take the solution. Okay, boleh faham tak untuk efisiensi ni?
Boleh?
Okay, it's good.
Kena buat latihan, Doktor.
Apa? Apa tadi? Afiq,
Kena buat latihan.
dah buat latihan?
Latihan. Kena buat latihan baru faham sikit.
Betul, itu memang memang betul lah. Okay. So the question mention a 15k VA. So this mean is the apparent power. Apparent power is actually at the output side. So output side, you see the VS minus VSIS. Okay. So apparent is SI equal to VSIS. Okay. And then this is the turn ratio. Okay, this is VP and this is the VS. Okay, and then transformer is to be tested, determine the excitation branch, its series impedance, and its voltage regulation. The following test data are taken from the primary side of the So and then they ask you to get the parameter for the impedance. Okay, and then calculate it, refer to the high voltage side, and then calculate it to the low voltage side. So high voltage side, you just refer here which one is the highest. So if the left one is highest, mean that the primary side. So refer to the primary side. Okay, and then this one lower mean that the secondary side. Okay, and then calculate the full load regulation. They say regulation at power factor 0.8 lagging, and then unity, and then at the leading. Okay, and then they ask you to plot the voltage regulation. Okay, they ask you to plot the phasor diagram. Okay, and then calculate the efficiency. Okay, so mana ni? Okay, so for the short circuit test, okay, we can directly go to the measure the angle or the power factor. Okay, so this one is lagging. Don't forget. This is lagging. Once you get everything you calculate using the test, short circuit or open circuit is lagging. Okay, always remember. So once you get the 84, the angle, so you can directly calculate the YE. So you put the equation, okay, and then put the calculator in mode I think complex, and also you can measure the real and imaginary part. So this is the GC, and this part is the BM. Okay, so then you calculate. So okay, so then you can get the RC and XM. Okay, so and then go to the short circuit test, you get the equation and you get the theta. Okay, and then you put the value in the equation. That one you will get the R equivalent primary side, and this is X equivalent the primary side. Okay, so no need to do already. No need to do the high voltage side. Okay, because it's already in the high voltage side. Okay, so you just transfer the to the secondary side. Okay, so this is the dia draw dia buat dia punya equivalent circuit. Okay, doesn't matter, you can put here or you can put here, the branch doesn't matter. Okay, and then you transfer to the secondary side. Okay, and then yeah, so we know that the S is the apparent power kan. Okay, so Vs Is, so they say that S is rated, so we S rated, Vs also rated, I also rated. Okay, S is, the value of S is 15k VA. Okay, so where to get the Vs? Okay, where to get the Vs? Here. Okay, this is the Vs rated Vs rated, which means the full load full load voltage. Okay, so we can directly calculate, and then we get the Is. Okay, so from the equation, from the Kirchhoff voltage law, ingat yang ni, from this kind of circuit. Okay, so we will get this equation. Okay, this equation. So we know that Vs, the phase of Vs is 0. Phase of Vs is 0 because we refer from there. Okay, so we have the component. Okay, we have already the component. So this is Vs, and this is the Re. Re. This is Is. This is Xeq. Okay, R equivalent. Equivalent. This is R equivalent. Okay. So we just measure everything. We will get the Vp over Va. Okay, we get the Vp over Va. Okay, and then we can calculate the voltage regression. Okay, so we can calculate voltage regression. Okay, just put everything. Ni 230, 230 from the given. Okay, so that we can get the voltage regression during the power factor 0.8 lagging kan. Okay, so and then they say calculate the voltage regression at the power factor unity 1. Okay, so we have the value of Is, so 1 mean that the angle is 0. Okay, so in same phase with the voltage. Okay, same equation, we just put everything, and we will get the value of Vp over A. Okay, and then we can calculate the voltage regression. Okay, so we can get the value. So from here we can see once the power factor lagging and unity, we will get the positive number. Okay, and then they say calculate the voltage regression at power factor leading 0.8 leading. Okay, so we can, same equation, we just put it here, the angle for the I. Okay, and then we just put everything again, and then we will get the Vp over A, and then we calculate the voltage regression. And we can see that the value when leading, the value become negative. Okay, and then they ask you to draw the phasor diagram. Okay, so we just draw follow the angle of the parameter. For example, the Vs, the angle is 0, and then the Is is negative 36.9. So this one is 0.8 lagging. Okay, this one is power factor lagging, and then this one is power factor leading. Okay, and then this one is at power factor leading. Okay, so I think that's it lah. Okay, yang bawah ni tak payahlah. Yang seterusnya kalau dia suruh plot tu kan, because dah ada masuk MATLAB apa semua. Okay. Oh, mana ni? Okay, and then for the three-phase transformer, I encourage you to watch the video. Okay, I will not cover in the class. Okay, so please watch the video. So we have another 1 hour left. So please watch the video. Okay, and I think we will go to the project. Okay, so before we go to the project, do you have any question regarding we just cover now? Okay, kalau tak ada, I think kita stop recording.
Doktor, test chapter berapa?
Chapter 1 dan chapter 2.
Sampai habis chapter ni?
Sampai habis chapter ni. Mungkin 3 phase tak masuk lah. Mungkin lah, mungkin. Tapi saya tak pasti sebab Dr. T yang buat. Okay, sebab soalan test pun tak buat lagi.